Okay, let's get started. Thank you all for coming. I'm Bill Freeman, Mark Hamilton's thesis advisor. So I'm going to talk for a few minutes and then hand it over to him. So it's been delightful to work with Mark. He's comes in with crazy schemes, art categorization via computer vision methods, and does them. And then, usually as a professor, if I'm going to propose something crazy, I have to do it only to an entering student, because by the time they're, a year or two in, they realize that not everything that we propose is going to work out. But Mark was willing to jump in and help me on something crazy, even kind of mid to late career. And that's, I think, because he knew that he could make it work. So I was, this is something that's not in his thesis, but I just want to mention it. I was working on this project where I was, as kind of a part of a workshop honoring a friend of mine, I was looking for images of that friend in random noise and in spaghetti tossed on the ground and stuff. And I was having trouble finding it. And Mark helped me out. He really bailed me out on this project, which was great. And we ended up writing really one of the most fun papers I've been involved in on pareidolia, the task of looking for faces in noise. And we combined computational, theoretical, human psychophysics. It was great. And in the grand tradition of ground truth labeling for computer vision, Mark's mother helped with the labeling of the data set. And Karen's here, and we thank you very much for that. We professors always acknowledge that we learn a lot from our students, and that's been emphatically true in Mark's case. It's, I've learned a lot from you, and it's been delightful working with you, and I look forward to continuing that collaboration as colleagues. So we look forward to what you do in the future. Take it away.
Well, thanks again, Phil. And yeah, thank you all for coming. Welcome to the thesis. I'm so glad that I get to share this moment with you all. So today we'll be talking about creating these kinds of algorithms that can discover interpretable and understandable things in complex systems, in systems out there in the real world with lots of bells and whistles and dials that we don't truly understand quite yet. So I'll kick things off with a little bit of a scientific legend about Dmitry Mendeleev. You might remember this guy from high school chemistry. He discovered the periodic table of the elements. That's his mugshot up there. And Dmitry Mendeleev had worked on this problem for like 10 years, studying chemical elements and really just obsessed with trying to order and categorize the elements of his day. And he had really toiled to try to organize and understand this system. One day he had the great idea to write down all the different elements onto cards so that he can really quickly prototype and arrange them and try to figure out the pattern. And even after he had this good idea, he spent, legend has it, 3 days nonstop, just arranging these cards all over the place until he collapsed out of exhaustion on top of his cards. And then upon waking, he said that he saw in a dream a table where all the elements fell into place as required. And he immediately wrote it down after that. So what does this tell us about how we discovered new scientific organizing theories? Well, to me, it tells us that it's really hard. It's absolutely terribly difficult. I mean, Dmitry Mendeleev worked for the better part of his life to organize this. He had built up intuition himself. He had almost the correct idea to write them down on cards. And then even then, it took him 3 days of shuffling them around. And even after all this, he still couldn't do it. He needed divine inspiration to come up with this periodic table here. So what if there's a way that we can kind of sidestep some of this stuff? It's really difficult for humans to understand the natural world, especially when they don't have a lot of intuition. I mean, these chemicals that Dmitry Mendeleev were shuffling around back in the day, I mean, it's like gobbledygook, right? No one had a lot of intuition about what these things were. It was only after the periodic table was kind of laid out that people started to understand a little bit more about the subatomic world. And so what if we can kind of use AI to help us get there, help us extend our reach to be able to make sense of systems out there in the natural world that we don't quite understand yet? So that's going to be kind of the central theme of this talk, is how we can use AI to help solve problems that we don't yet know how to solve. And this talk will be structured in roughly 3 parts. One of the parts will be about how we can understand how to build these kinds of systems. What are the key theoretical insights to make systems that can learn without any human input whatsoever? And then once you understand how to build these systems, then you can actually go about building them. So how do you build them in practice? How do you actually understand these complex systems? How do you validate them on systems where we already know the correct answers so that we can make sure they're learning the right things? And then finally, when you're really confident, as you've got good theory, good experiments, good systems, then you can try to apply these to systems where you don't know the answers a priori and try to understand a little bit about the natural world. And so these will be the three parts of the talk, and we're going to go out of order, of course, because when you start your PhD, you really have no idea what you're doing. You have no theoretical background or anything like this. You just got to build something and get it out the door for the first publication. So that's where we'll start in the middle. We'll see two different algorithms here that understand complex systems without any human input whatsoever. The first will be an algorithm that takes a pile of images and classifies every single pixel of these images without any human input. And the second will be an algorithm that just watches a ton of videos, and from this rediscovers the meaning of language, the meaning of words, the meaning of adjectives, things like this. And then once we've seen two examples, we'll try to develop some theoretical insights here to understand a little bit more about what's going on. So we're going to dive into a little bit of the theory behind how to build these classes of algorithms. And in particular, we'll present a single unified equation that combines roughly 23 plus different machine learning methods out there into one equation. And this will be the basis for our periodic table of machine learning that we'll talk about a little bit later. And then finally, we'll try applying some of these techniques to a domain where we don't really know the answers yet, which is translating or trying to decode animal communication, specifically that of the Atlantic Spotted Dolphin. Now, I'll set some expectations straight here that we haven't done this yet, but this is going to be some preliminary and ongoing work that starts to chip away at this problem a little bit, and we'll see a little bit about what that looks like. So, without further ado, we'll kick things off on the first section, which is we're going to build an algorithm that can understand the visual world without any human input whatsoever. So the basic gist of this algorithm is that we want to take a big bag of unlabeled images, and we want to create a little algorithm here that can take a look at these images and come up with A, a set of objects that it sees in these images, and B, a way to take any image and classify every single pixel of these images into that ontology of objects. And because there's no humans in the loop anywhere, we want to be able to apply this to any collection of images and have it come up with something reasonable, something that a human would have come up with if they spent all the time figuring out what's going on in this data set. So we want to be able to apply this to any kind of domain. And you might be thinking how on earth do we build such a system? We have no human labels. We have nothing to tell the algorithm about how to solve this problem. What could we possibly do in order to make a system like this? And so that's what the first section of this talk will be, is a little bit of an insight into the games that we play in order to create algorithms that can learn with zero human input whatsoever. So ordinarily you have labels, you have actually a word, dog, and guitar that goes along with the images. But what happens when you don't have this, right? You have to get a little bit more clever with how you get your algorithm to learn. So we're going to play a little game here. We're going to take these images and we're going to chop them up into different puzzle pieces, so to speak. We're going to take them, we're going to crop them, transform them, change their colors, rotate them a little bit. And we're going to make a few example images here. I've made 4. And now the task that we tell our algorithm is a matching game. We ask it to find which images go together. And our goal is going to be that we want to train this little machine brain in order to solve this task efficiently. And you hope that after this training, it properly matches 2 and 4. They're both pictures of guitars from different viewpoints, and 1 and 3, they're both different pictures of that dog. That's what we hope the algorithm will learn. And so what exactly do I mean? How do we actually do this? Well, we have our little robot take a look at each one of these images and write down a few numbers. These are kind of its ideas about what it's seeing here. And they call these deep features or deep representations. This robot is kind of constrained to beeps and boops, so it's just going to spit out, 50, 1,000 numbers here for every single image that it looks at. So I'm going to take our little robot, it's going to look at every image, and it's going to spit out these strings of numbers. Now, That's the kind of first phase. The second phase, the training phase, is that we're going to tell the algorithm how it could improve those strings of numbers. And in particular, for the images that we know belong together, that we've cropped and messed up, we're going to tell them, you should have written down almost the same numbers for these two pairs of images. And for the images that come from different original images, we're going to say, these should be as different as possible. If you wrote down the same set of numbers for these two images, incorrect. And so the algorithm is going to do this thousands and thousands of times over hours and hours. And slowly but surely, it's going to get better, and it's going to learn a consistent way to write down these numbers so that it can always solve this task quite well. That when it's given two images of roughly the same thing, like say these two images, it will output kind of similar strings of numbers. And the surprising thing is that this actually works in practice, that here with these two images, even though they're different dogs, they're different colors, they're different poses, they're different positions, after you train these kinds of systems, they actually start to understand that this is, roughly a similar object between these two images, which is kind of a miraculous finding to begin with. But it goes a lot further than that. They don't just understand that these two things are the same kinds of object. If we actually peek into their brain and open up and look at what they're looking at, we'll see something that looks like this. We'll see objects glowing in their neural representations. And entire objects, no matter what their colors are, will just glow and be perfectly almost segmented here. So it's almost like these algorithms, in order to solve this matching problem, have to solve a lot more than just that matching problem. They have to figure out exactly where the objects are, how they're structured, which are different objects, which are similar objects across the entire image. And so this is kind of the first observation we made in this paper. And our goal is really now to take this, which is almost the correct answer, and massage it a little bit and crystallize it so that it actually is one of K classes in this data set. So that's what we'll be talking about today. And in terms of a little bit of detail about what this brain surgery procedure is, we have to dig a little bit deeper. Modern image networks, there are these things called transformers. They take an image, they split it up into a bunch of little patches, and they pump these patches through these big transformer architectures. These are the same kind of things that large language models are built out of. They're like a differentiable Python map kind of thing. And so they take all these image patches and they add on an extra patch called the class token up there, and they pass them through this big transformer, and you get a ton of numbers that come out of this system. Now, ordinarily, people just take one set of these numbers, the numbers associated with this global class token, and they use this set of numbers to play the matching game. And what do they do with all the rest of the numbers? Well, they toss them in the trash, right? Who needs them? And what we found is that you can actually fish these out of the garbage, and these are these really smart neural representations that these algorithms tend to learn. And ordinarily, people just toss them out. But what we found is that these are actually encoding where the object is and telling us what's the same object and what's different objects in an individual image. And you might say this is a little bit lower resolution than the picture I showed you before. We have another paper that I don't have a chance to get into that will make it pixel perfect, that will take it from 16 by 16 and blow it up to 224 by 224. I don't have a ton of time to go into that one, but well, shameless plug here for that paper. So now that we kind of have this method of almost pulling out objects, that you pull out these numbers that are really, really well correlated with an object, we now need to turn this into one of K classes. And to do this, we take an image, we get these fancy features out, these fancy representations, and then what we're going to do is train a little tiny classifier on top of them. And the training signal is going to be super simple. We're going to take a few points in this image. Here's 3 random points here. And we're going to say for the points that share the same features, that have the same color in their representation, those 2 pink points here, we're going to ask that these 2 points have the same class. We're going to say whatever you learn with that small classifier, we want to make them the same class. And likewise, if 2 points have very different neural representations, we're going to tell that classifier these should probably be different classes. And that's the kind of the intuition about the training signal for this particular algorithm. It's really about looking at relationships between features and then learning a set of classes that respect those relationships. That we don't want to break up friends in feature space. We want to keep them together in classes. And this very simple technique works surprisingly well. So here I'll show you a little bit of results. These are just some images. These are the labels that have been painstakingly human annotated for exactly what everything in these images are. And this is the best baseline so far before our work. And you can kind of see that it gets the gist, a little globby, sometimes it misses the object entirely. In comparison, this is the results when you do that kind of very simple feature distillation approach. So you can see that it gets some of the objects that previous methods miss. It has a lot more fine-grained details here. It can pull out each individual swan in these images. And this doesn't just result in a nice qualitative boost, prettier pictures that better align. It kind of doubles the performance of these systems. So it doubles the mean intersection over union, which is a classic way to kind of measure how well these algorithms perform. And it not only works on sort of standard images that I've shown, but it works on kind of driverless car images and aerial images as well. So no matter what kind of domain you apply this sort of algorithm to, it will almost rediscover the same kinds of objects that humans have painstakingly discovered over their millions of years of evolution. So that's kind of the first algorithm here, that you can give it a whole pile of images and then extracts out these really interpretable things that align with human judgments, but without a human in the loop whatsoever. The second algorithm that we'll cover is an algorithm, it's weird, slides are a little poorly rendered here. But the second algorithm that we'll talk about is an algorithm that rediscovers language just by watching videos of natural scenes. And so in order to kind of get an understanding for how this works, we're going to play a little game here together. So in particular, I'm going to play a little bit of non-human language, and your job will be to figure out what that thing is talking about, right? And so this might not work super well in the AV, but we're going to try it out, and we'll have to be quiet here. So I'm going to play the clip. All right, so what did it say? Anyone have any ideas? Huh? Anyone? All right, yeah, kind of really difficult to figure this out, right? But the secret comes in that when you actually see what's going on, everything becomes a lot clearer. So I'll play this clip. Yeah, so now it becomes very clear that this is penguin for, God damn it, that hurt a lot. This is and there's a little bit of magic that happens here, right? Like you get something that you couldn't understand before, that you really have no idea what's going on. And then when you actually get to see the frames, suddenly it starts to make a little bit more sense. And this is what this algorithm is going to exploit. It's going to exploit the relationship between audio and video in order to rediscover the meaning of language without anyone telling it what the meaning of words are, how people in English speak, etc. And so the game is going to be very simple, very similar to the image matching game. We're going to take these videos here, let's say a guitar player and some cows, and we're going to split them up into audio and video signals. And then we're going to play a similar matching game. We're going to tell the algorithm things that came from the same video belong together, and things that came from different videos do not belong together. And it's going to do a very similar style approach. It's going to write down a string of numbers for each kind of signal, and it's going to try to play this matching game together. And as you scale this out, as you give it millions and millions of videos, this game gets really hard to play. It gets really hard to match images and audio, and it's kind of forced to understand the meaning of language as a result. So this isn't new by any means. Like people have done this in the past. There's a notable paper called ImageBind, which is, does this at massive scales from Facebook across a ton of different modalities. So, I'm lazy. Let's just try it out and see if it works. So take these two images, we pass them through this ImageBind model, we get these collections of numbers, some for the spatial tokens, some for these global class tokens. And these global class tokens, just like in the image example, this is what they use to play the matching game. But let's fish those local features out of the trash and see if they can actually localize the sound. The surprising thing is that when you do this, you find that they do not localize the sound. You get images that look like this, where I can play guitar and the whole image will light up, but the guitar won't light up. So there's something missing here when you look at these state-of-the-art algorithms. They don't properly localize things in quite the way that you might want. They don't allow you to rediscover the location of sounds or the meaning of language just out of the box. So we need to do a little bit of tinkering, unfortunately, to get these things to work well. So if we think about what the issue is, we look at the architecture, they're just slamming together these two global tokens and hoping that the local tokens will look very nice as a result. And for the image case, it happened too, but it doesn't always have to happen this way. So how can we fix this? If we think about this implicit trash can full of local features, if we dumpster dive a little bit and pull those back out, we can see that they're actually quite smart. And instead, what we're going to do is, instead of slamming together two class tokens, we're going to look for matching regions between these local features. So here in this case, we want it so that when someone says the word dog, we want to see it coupling nicely with that image of a dog over there. We want to find these matching regions. And the idea is that if these two clips go together, there should be a lot of matching regions to find. So that's going to be the crux of the way that we're going to play this matching game. Instead of just writing down one string of numbers, we're going to write down, a lot of different numbers and try to find matches within them. For a little bit more technical details, the way we're going to do this is we're going to take these numbers and we're going to form all pairs inner products to get this audio-video activation map. And we're going to aggregate this down via some average pooling and max pooling to get a single measure of similarity between these two images and audio clips respectively. And surprisingly, this is kind of, once you start actually doing this contrastive learning with these local features, suddenly everything looks a whole lot nicer when you stare at kind of why it's finding these matches. So I'll briefly share a few examples. We'll see if the audio works, because
cools itself in the river.
Let's see if we can restart it here.
The elephant cools itself in the river. It watches the trees for predators.
So hopefully that was aligned. But basically the idea is that whenever the word elephant, maybe this view is a little bit easier to see, when the word elephant is said, you see that the elephant glows with this kind of activation. When the word river is said, the water glows with that activation. When the trees are said, the trees in the background will glow. And you can even see this if you look at a PCA representation of these features, that the elephant's purple, the elephant in the language features are purple. So this is that we can actually probe into this algorithm and see it rediscovering language in order to solve this matching game. But we didn't actually tell it anything about how to parse the word elephant, or even that there was a word elephant. It just kind of rediscovered these correlations between speech and vision automatically, just from playing this matching game. And this works not only for nouns, it also works for adjectives.
On a wooden cutting board. Cut the peppers on a wooden cutting board.
Yeah, so you can kind of see when she says wooden, the wood area glows pink. And that's kind of showing that it not only learns nouns, but some adjectives as well. We have another version of this algorithm that can even disambiguate the location of sound and language here. So this is a clip where we've given the algorithm kind of two heads, and one of the heads just automatically discovers sound and the other head automatically discovers language. So I'm coloring the sound head blue in this case and the language head red, and we'll see in this clip. Let's restart it so that the audio is better.
It's okay, puppies. It's just the snow.
Yeah, so you can see when the puppies bark, then the sound head is going to turn on. And when she says the word puppies, the language head will turn on. When she says the word snow, the snow in the background will start to glow. And this is like entirely rediscovered by the algorithm. We didn't really tell it about the separation between sound and language. The algorithm just thought this might be a useful way to organize my internal mental states to try to solve this problem. So you can really extract a ton of blood from this stone with very little human labels entirely. So that's kind of the key gist of these two works. And now we'll see a little bit about what's going on behind the scenes. What's the theory behind why this works, and why are both of these algorithms able to kind of discover such rich structure? In particular, we'll introduce a single equation that unifies like 23 plus different algorithms in machine learning. It forms the basis of our machine learning periodic table. And at this stage in the talk, I got to warn you, like, there's going to be some math. I'm really sorry. I'm sorry to say. I'm going to try to make this as fun as possible. I'm not going to subject you to proofs. And maybe we'll start off. I'll give you a little tour of machine learning. There's kind of a zoo of different methods out there. So we're going to enter the machine learning zoo here. And we're just going to talk about some of the different animals here and what they're like. So to start, we'll look at our giraffes and our porcupines. These are our classic classification and regression algorithms. These are algorithms that do things like determine whether an image is a cat or a dog, or predict the weather tomorrow from the weather today. Over here, the parrots, those are the LLMs. Like, you know, if you've done homework after 2022, you kind of know that these LLMs are really smart and they're good for everything. And so these LLMs, they're basically like a fancy classification. They predict the next word from the previous word, more or less. Coming over here to the zebras, we're starting to get a little bit more unsupervised. These are the clustering algorithms. They take collections of points and they group them together based on how similar or close they are. The hippos over here, these are dimensionality reducers. These are now getting a little fancier. These things, they take high dimensional data and they compress it into a smaller number of dimensions. Like if you look at this little Swiss roll cake here, what dimensionality reduction will do is it'll unroll the Swiss roll back into a little sheet cake so that you can determine where you are on that Swiss roll with 2 numbers instead of 1. Spectral graph theory here, if you've ever done like internet analysis or social network analysis, this is kind of the theory that's about graph Laplacians, graph eigenvectors, and things like this. It helps you understand and map large social networks. And finally, our gorillas over here is our contrastive learning systems. These are our systems like what I presented in the first 2 examples that play matching games of various sorts. They take images and augmentations and try to pull them together. And yeah, so you can see there's a ton of different algorithms out there. Each one of these big boxes holds like, I don't know, 50 to 100 different algorithms. And you might think, you walk into this zoo that like, wow, what a diversity of animals. I love all these exhibits. I'm gonna have a ton of fun looking at all these different animals. But the surprising thing, and what this theorem says, well, what these 15 theorems say, is that this zoo is not comprised of different animals. It's really just comprised of like a bunch of gorillas wearing different animal costumes. So the kind of idea behind this work is that contrastive learning is secretly all these other methods, and you just don't realize it. And if you do the math properly, you can kind of see this quite directly. So that's what we're going to show at a high level. And now fun's over, guys. Like back to math. So we're going to start thinking about one of the simplest ways, which is dimensionality reduction here. I've got my little Swiss roll cake in 2 dimensions, it's a little 6 here. And what we want to do in dimensionality reduction is that we want to learn some fancy brain, some little algorithm to take this cake and unroll it into a line. So we want to reverse the process of the Great British Bake Off and take that swirled Swiss roll cake and flatten it out. And how do we do this efficiently, and how do we do this in a good way? We want to keep friends together. We don't want to break up any parties. We don't want to put any enemies next to friends. And what that means mathematically is that we're going to take a little Gaussian around our points in high dimensions. This is going to be like a soft notion of friendship. And we're going to stick a little Gaussian around our points in low dimensions. And what we want is that, you know, my friends in high dimensions should still be my friends in low dimensions. So we want P and Q, these 2 distributions, to be as close as possible together. We don't want to break up the party as much as we can. So there's really one classic way to do this, to encourage 2 distributions to be very close together, very similar, and that is the KL divergence. And we're going to sum over all the different data points. That's that outer sum there over I. And so that's the basic gist here. And this is actually an existing dimensionality reduction called SNE. It's later generalized to T-SNE, if you're familiar with that. It's like a classic way that you view high dimensional points. And this is sort of the standard story, and usually this is where it ends. But what we'll show is that this equation right here is kind of the secret general equation that all sorts of other things fall out of quite naturally. So the key idea here is that we're going to replace what it means to be friends, and we're going to see that as we change this notion of friendship, we start sweeping out all sorts of different algorithms out there in the world. So first, what I'm going to do is that I'm going to replace these high dimensional Gaussians with a discrete distribution that's going to say take 2 images and connect them together if they're augmentations. So this is kind of that matching game that I've shown earlier in the slides. And lo and behold, when you put this into this equation and you run the numbers, you simplify this equation down, you get that this is equivalent to the info NCE, which is the classic loss function used in contrastive learning. It's like the official one, the best working one. So you get that contrastive learning is actually secretly dimensionality reduction, which is quite an interesting observation. And this observation, you can just keep doing this trick again and again and again to start sweeping out other methods. So here, I'm going to take high dimensional Gaussians on the left. But instead of low dimensional Gaussians on the right, I'm going to replace it with cluster probabilities, probabilities that you're in a certain class or cluster. And here, I no longer need Gaussians to tell you when 2 points are friends. I can just say 2 points are friends if they're in the same cluster or class. And when you put this into the equation and you simplify the math, what you find is that your loss function is equivalent to k-means. This classic clustering algorithm that's been around for like 50 years, probably used like millions of times throughout the last century. So it's this classic canonical clustering algorithm that everyone knows and loves. And no one realized that this came out of dimensionality reduction. You can go again further. If I swap out high dimensional Gaussians for Gaussians on graph edge weights, you find that this is equal to normalized cuts or spectral clustering. So don't worry if you don't know what this is, but it's a classic graph clustering algorithm that people know and love in the graph community. And so we've seen a few different things that go into these boxes here: Gaussians, classes, edge weights. And if we start putting these into a little table where, let's say, the P distribution is on the columns and the Q distribution is on the rows here, we can plot where all these different algorithms fall into this little mini periodic table here. So these are the ones that we just covered here in this talk. And you'll see quite suggestively, there's 2 holes here in this table. And we're going to ask the question of what's in that hole right there. So if you think about what's in this hole, it's going to be a combination of contrastive learning and cluster over here. So let's do that. We can kind of have it learn cluster probabilities and have it learn from contrastive supervision. And we can optimize that loss function. And what do we get? We get a state-of-the-art image clustering algorithm that falls out in this hole. And so this, it's really interesting that in this hole where this periodic table predicted the existence of a new method, you get something that's very reasonably defined and performs quite well, actually state-of-the-art for rediscovering the labels of ImageNet without any human supervision at all. So that's kind of one hole that we fill in this paper, but this table actually gets a lot bigger. So this is the full size of the table here after you start thinking of everything else in machine learning and whether it can be squeezed into this framework. You find that like 23 plus things can be squeezed into this framework here. So this is the full size of the table. You'll note that these 2 cells are the 2 algorithms we covered in the first section of the talk. First one is the unsupervised semantic segmentation, classifying every pixel. This one is DenseAV, the rediscovering language from watching videos. So those 2 algorithms fit nicely into the periodic table. If you squint your eyes and try to fill some of these holes, you can roughly, get a sense for what's missing here. And everything else that is kind of opportunities for you all or other people in the field to fill. So there's still a lot of interesting real estate here in this table that might yield a paper or 2. So I also want to call out that the real Dmitry Mendeleev of this work is sitting here with us today. That's Shadin. She's our lovely master's student in the back there. Absolute genius, like powered through like 15 plus theorems to make this paper work. And big congrats to her for getting this into iClear this past year. So great. Now we've kind of seen a little bit about the theory, a little bit about the practice. Now, thanks for sitting through that. And we get to the fun part now. There's this old saying that like when you start your PhD defense talk, everyone's kind of following you, right? They're following along, and somewhere along the talk, you lose half the people. And then it kind of like keeps going. You like lose half and half and half until the very end, even you have no idea what you're talking about. And that's this section of the talk right here, that we have no idea what's going on with these dolphins, but we're starting to chip away at it, and we'll show some preliminary analysis of this. So this work is done in conjunction with the Wild Dolphin Project. They're a nonprofit that kind of has spent 40 years diving with the dolphins, videotaping them, recording their audio, and really aims to learn more about dolphins so we can better conserve them. And it's so footage that they captured, spectacular footage. This was from our trip when we went out there last year. Be able to hear some whistles in the background. They're very high frequency whistles, and they're kind of hard to hear, but algorithms can pick them up and amplify them and bring them down to human hearing. And so this is kind of roughly the data that we have to play with. We've got like 40 or maybe like 50 or so hours of this kind of video data. And now what we're trying to do is really make sense of this data, see if we can apply some of these techniques that we've both covered theoretically and practically to try to chip away at what these dolphins are saying. So, we've covered one algorithm that can rediscover the meaning of language just by watching videos. That's DenseAV, the second algorithm we talked about. So can we apply that here, right? Like, what if we just try it? Unfortunately, that does not work. There's not nearly enough data. We've got like 2 orders of magnitude less data. And, the dolphin world, it's got a whole lot less nouns, possibly, than our world. And it's a lot more focused on behavior and relationships between dolphins and configurations and things over time. So that's a little bit harder for these kinds of algorithms to pull out. So our first attempt, this kind of matching game, it couldn't do better than chance. It was just basically random guessing, and that was it. So we had to go back to the drawing board and had to think about like what else can we do to kind of make this a little bit easier to learn. So, what we ideally would want is some dolphin expert to come and annotate every single frame of this video by hand. And Denise and her team at the Wild Dolphin Project have done some of that, but they have like more important things to do than label every frame of dolphin by hand. But I can think of one person who doesn't have more important things to do, which is ChatGPT. We can take ChatGPT and it's smart. Like, it's quite smart, especially when you ask it the same question 10 times in 10 random shots and average the answers. That can really cut down on a lot of hallucinations. So we can give these frames of this video to ChatGPT, and we can ask it whatever we like. So we worked with the Wild Dolphin Project to come up with a prompt that asks it like 60 plus different questions about these videos of dolphins. Like, are they digging? Are there juvenile dolphins? Is there seaweed? Are they splashing? Are they fighting? Are they having sex? Like, all sorts of different things we can ask ChatGPT. And, it's reasonable. It actually does a lot better than you might expect. Like, these are some of the examples of things that ChatGPT has spotted in this data set that are not cherry-picked. So this is the random seaweed example. This is digging in the sand. This is breaching out of the water, jumping. This is juveniles. We were really surprised when ChatGPT could figure out what a juvenile dolphin looked like. This is group diving behavior, even looking at the camera, checking out the snorkelers down there. So these are some of the examples that we've been able to find in this data set. And the awesome thing is that we get about like 4.4 million of these almost expert labels in 24 hours, because ChatGPT is just voracious and tireless. We can just prompt it millions of times and it's fine. And also big kudos to Microsoft for letting me do this, letting me spend their ChatGPT budget on this. So now with all of these different almost expert labels, we can think of a slightly more data efficient model. We're going to do this same matching game, but instead of matching instead of training some big fat video network to make sense of these video clips, we're just going to train it to match against all these different questions that we've asked it. And this particular algorithm, because it's just a lot simpler of a problem, does about 17 times better than chance at matching dolphin audio to video. So it learns a lot of non-trivial things, enough to make it 17 times better than chance. And now, this is where I kind of leave you, that now we have to figure out how in God's name it's doing this. Like, what is it using to get 17 times better than chance? So we can kind of look at these features and we can start to, this is kind of a view of the brain of this algorithm. And every single clip here is kind of plotted in the brain. And the clips with whistles are colored yellow in this image, and the clips with clicks are colored yellow in this image. And what you can kind of see is that different regions of this brain light up, kind of connoting that it's separating it in its mental states between whistles and clicks, which is a reasonable sign. These two forms of dolphin communication are used in very separate contexts. Clicks are mainly used for echolocation, and whistles are used for more interpersonal communication. So it's good to see that these kinds of different communications are starting to split apart in this algorithm's representation of the world. And for the next few months, we'll just be trying to color this plot in different ways to understand, like, are there any localized regions for seaweed, for fighting, for pooping, for anything? so that we can start to say, like, is there can we find at least one dolphin word using this sort of technique? So that's kind of where we are right now, and you'll have to come to my next thesis defense to find the next set of answers. So just to kind of briefly recap what we've covered kind of this unified theorem that connects all sorts of different machine learning methods together and forms a periodic table of machine learning. This tells us a little bit about why some of these methods work, that there's a really interesting interplay between relationships between data, that it's almost like what this equation says is that the relationships, the friendships you make along the way are the most important things for machine learning. And you kind of see this happen in two different contexts, both in the context of predicting visual objects without any human labels, and also predicting the meaning of language without any human labels. And finally, we've seen a little bit about how this can start to tell us something about dolphin communication. We're still in the very early stages of this project, but I can't help but share it. So, and that's kind of the last phase of true academic content. So I'll stop here for questions, and yeah, please feel free to ask. Like, don't be bashful here. So. Yes.
I'm sure this is complicated, but I was wondering if you could speak on differences between stego and multiplication.
Yeah, that's a great question. For those online, the question was like, what's the difference really between stego and dino? So the way that I think about this is that, let's see if we can get back to that slide a little bit simpler. Here. Yeah, so some of the gory details behind this is that self-supervised model, that's Dino, right? And it spits out these really smart features, and we keep that frozen in Stego. We don't adjust that backbone because it's already really smart. We don't need to do anything. So what Stego does is it trains this little tiny classification head, and the idea is that these features, they're almost there, right? They're almost at a consistent set of objects and classes. They're just soft and squishy. And we need to do is harden them up into one of K classes. And so that's what that classification head does, is it takes those features and it hardens them up. Instead of outputting 1,000 numbers, it outputs a probability distribution over K classes. And that's what it outputs. And its supervisory signal is kind of like Euclidean distance over there in feature space. So that's sort of where it falls in that periodic table, is that the supervisory distance on one side is Gaussians over here, and the learn side is classes over here. And it's done on a per pixel level as opposed to like a per image level. So does that answer your question? All right, keep it coming, guys. Let's go. Yes.
I'll try to make this make sense. So I like the penguin example where you take some mode of data, you hear it, doesn't make a lot of sense. You give the second mode of data to have a context of the two, you
Yes.
functionality. For lots of works, it's the data that we have is a lot of images, audio, and text. That's kind of the focus. But people and animals in the world, like touch and feel, and we take actions, and there's reactions. Do you think that there's something to, like, we're missing a lot of information that natural systems use that could be useful for building better artificial systems? We're kind of missing lots of it. How do you think that there's anything? I know there's lots of threads in that.
Yeah, I mean, I feel like yes and no, right? Like, I feel like it's hard to get, full notion of causality from just still images, but you can get like a surprising amount of that from just still images. Like someone in the group shared this really like thought-provoking image. It was a picture of a flock of birds, right? And then the idea is that you see a bunch of different birds and they're in different points of flapping. But from looking at those birds, you can kind of reconstruct what a bird flying would look like, because you see it at all these different points of time, even though you're seeing multiple different kinds of birds. So just from a single image, you can like roughly start to reconstruct motion. Now, like, this is going to be different than like a true causal world model, but it's a little bit of like a sign that like sometimes there's a lot of interesting structure hiding in data that you don't even expect there to be. And like how, I don't know, some folks here in Antonio's group have probed like large language models and shown that they like know about the visual world, even though they never see images, they just read text. So I think there's a bit of that like, you know, as long as you have enough data that's reasonably rich, you can start to chip away at some of these other forms of modality. But for sure, it's like if you put in these causal structures directly into your algorithm, if you train on videos directly, you know, you don't have to squint your eyes to see these kinds of patterns. They're just directly in the data. So you probably would get a lot of, you probably would still get some amount, but maybe my answer is that you probably would get a little less than you might think, just because so much of this is already in images, let alone videos. Yep. Yeah. I think that's a very good question. So for those online, the question is like, you know, how does this like roughly handle like correlation, right? That in some sense, and maybe my answer is that I think a lot of it is correlation based. Like it's certainly going to be, because it really has no causal levers to pull. It can't like move that duck into a conference room. It really has to rely on like seeing images of ducks in conference rooms. But I think that also helps it learn a good amount, in the sense that like, there's this saying in language that like a word gets its meaning from the company it keeps, where if you have some word like dog and you have another word like puppy, they appear in all the same contexts. They correlate with the same things. Like, I'm going to go to the park to walk my dog. I'm going to go to the park to walk my puppy. And in some sense, that's what like gives it its meaning, is the fact that it shows up. It's interchangeable with dog and puppy. And there's some times where you use puppy and you can't use dog. And that's hopefully enough to like get an algorithm to disambiguate a little bit. But I think it will certainly make, like we have an example for the limitations where it's like a banana on a phone receiver, and it certainly does mess up in these contexts where it's very out of distribution. It's like almost adversarially composed and things like this. Sometimes though, with enough data, it kind of comes out in the wash though. As you kind of see with these massive diffusion models, that they know how to put bananas on phones now, and it all works out well. Yeah. Yeah, that's a very good question. The short answer is that we didn't really look into that. The long answer is that, like, you know, what we did in DenseAV is that we didn't actually train on videos, because I was feeling very lazy in this project. We trained on single images. And so you don't have a lot of motion cues to kind of disambiguate like which person is talking or which dog is barking, which is why when the dogs bark, they all glow. If you train with videos, you can probably do a little bit better. And you can probably start to disambiguate like individuals that are talking and things like this. But we didn't try this like looking at an image where a person is talking and also a person is talking about something, whether both heads will light up. One of the things we did to get really nice results and really nice disentanglement between the two heads is that we added this regularizer that said, when head one is lighting up, turn off head two. And that like works very nicely to get very pretty results, but might also mess with that ability to simultaneously like have the sound head pick up on the people and the language head pick up on the things that people are referring to. So there might be a little bit more you need to whack that algorithm to get it to truly work like that.
On the icon section itself, you said you picked Dale because reasonable distributions.
Yes. Yeah, so just for everyone online, the question was like, why KL? What does that induce? Is the asymmetry important kind of thing? Are there any other choices? So that KL is chosen because that's what kind of unifies most of the different algorithms. But one of the things I swept under the rug is that the direction of the KL is quite important. Like clustering has it in the other direction than, say, representation learning. And this is probably to avoid blowups and things like this. We tried other kinds of things like symmetrized versions like Jensen-Shannon, and they seem to work reasonably. They didn't give us bolder columns, so we didn't really talk about them in the paper, but they still worked. But I think in the future, we're going to try to Wassersteinize the hell out of that paper because it's just better in every way, right? Like, I mean, I'm a Wasserstein zealot, so. Yeah.
So in icon, we unified everything by massaging all these different things into the same format, versions. One would think that would imply that they're all equivalent to each other and we could massage any of them in the form of any other. Yes, no, is there something special about the form that we chose?
Yeah, I don't know. I think like, I don't know if there's a way that you can swap the order of a KL generically. There might be. I think if that was the case, then you would change the neighborhood structure. You'd have to change the neighborhoods in order to swap the direction of the KL. So your interpretation of the neighbors might be very different.
No, I mean, we showed the, for example, spectral clustering scale. We showed the k-means scale. So could we take spectral clustering and frame it as k-means? Like, since they're all equivalent.
Yes, this is
that one form.
Yes.
Is there anything special about that form, or is this just one of the many forms that they can all be printed?
That's a very good question. Yeah, I'm not sure exactly. Like, one thing that you can show is that because all these methods are like woven together into this web, you can take techniques from one algorithm and apply them to other algorithms. But whether you can kind of take k-means and like reshuffle it, I think is, I don't know, it's a trippy question, right? Like you might be able to, if you're really smart, like you might be able to kind of say, this is like a softening of the clusters here. But you might generalize k-means so much that it just still looks like KL, right? Like
my gut feeling is that the answer is no, like
yeah.
They're special cases, right, that are equivalent under that parameterization, but we cannot take one out and turn it into the form of another different special.
It's an interesting question. It's like I don't know, like a complexity class style thing where you could ask the question of, are all these things the same if you squint your eyes? Yeah. Yeah. Next paper, baby. Cool. And I think Theo, you had a question. Yeah. Yeah, so the question is for dense AV, like, do we use speech to text or do we just use the raw audio? And we just use the raw audio. We make no assumptions on the structure of speech and language. What we use is a model called Hubert that just like self-supervised model that just listens to a bunch of speech and learns a good representation for it. And we fine tune that a little bit. So the hope is that like with dense AV, a human has never touched anything in the whole stack. And none of the pre-training was touched by humans and none of the alignments between these things were touched by humans. No text was seen in the process kind of thing. So that's why we chose that particular backbone, so that we could theoretically have the possibility to do it for dolphins later on, because we never really wanted to translate humans. We really always wanted to translate dolphins, and that was the impetus for that work. Cool. So I think we're probably running out of time for questions. So now we'll get into the crying phase of the talk. Yeah, so there's a ton of people that I'd like to thank today. It takes a real village to get a PhD, and maybe first I want to give a big shout out to my committee here, Vincent and Phil. These are like my academic superheroes. some of the smartest people I know. They're literally gods in the field of 3D vision and unsupervised learning, respectively. Now they're probably gods in like 4 more fields too. And I've just learned a ton about how to think about these different domains through conversations with them. I've learned a ton about like how to structure research by talking to them, and like how to pick a good research idea, how to think about research in a good way. And just huge thanks. And sorry for subjecting you to this 260-page behemoth you got to read between now and the end of the week. But huge thanks to you guys for all the academic insights and wisdom that you've given me over the years. I'd say the star of my committee here is Bill. When you start your PhD, everyone tells you that it's just going to be a gauntlet. It's just going to be this hellish ordeal of pain and suffering that you make it through in order to have better times later in life. And that just couldn't have been further from the truth. And I really owe that to Bill, that I really could not have asked for a better advisor. He's caring, he knows his stuff. He's been in the field for like 40 years. He gives you this high level feedback that's just these pearls of wisdom honed over the decades. And I've learned a ton about like what it means to be a good manager, a good leader, from just like watching Bill lead. I'm so lucky that I got you as an advisor, Bill. Like it really, it made this one of the happiest periods of my life. So thank you. Bill wasn't the only mentor out there in this world that kind of helped me get here. There's been a ton of people in my life that I really owe the majority of my life to, starting from high school with Herb Weiss, when he got me into science research and set me up with John, who's at MIT, who was kind of the first person who taught me calculus and took me from a potato to something somewhat less of a potato, and really spent that time to clock in the effort with me, even when I knew absolutely nothing about research. Further along the line, going to Microsoft, I had the help of an amazing boss and best friend, Sudarshan, who got me here and helped me start the PhD and work at Microsoft. He taught me how to be a good engineer, how to navigate the politics of Microsoft, how to dream big. Set me up with 2 other mentors, Anand and Joseph, who wrote my letters along with Sudarshan for the PhD. I got to give a huge shout out to my bosses at Microsoft now, Marcus and Avrilia, for giving me a safe home to work and do my PhD while I'm at Microsoft, and being patient with me as I do that. And here at MIT, I've had a lovely amount of great mentors. John, who's here today, Andrew, Simon, Marcus Kozowicz from Microsoft. These folks have kind of given me a ton of mentoring and support and guidance throughout the PhD, and I'm really indebted to them for this. So huge thanks to you all on this slide. It really also takes like a village to get a PhD outside of just direct mentorship and things like this. There's a ton of people who really make everything work out on the back end. So big thanks to Roger for organizing this whole event and party, to Joel for giving me delightful academic advice over the years and great conversations about einsums, Janet and Leslie for kind of running the entire graduate program here, for Rachel, Alex, and Adam, at MIT and CCEL News, that I always say that a paper these days, the paper's impact is like 40% like what's in the paper and like 60% how you drop the paper. And I would argue that means that 60% of my citations are because of these 3 folks up here in the media team. So huge kudos to them. Also, when you're doing your PhD, very few of the ideas come from your brain, right? Almost nothing originates inside your brain. It's really like a circulation of ideas around the community. And, I was really lucky to be in Bill's group because there's just such a broad community over the years that have been in these group meetings, that have shared their work, shared their ideas openly. And it's kind of kept me from becoming a dinosaur. I mean, I still am a dinosaur, right? But it certainly stopped me from becoming a fossil. And it's just, I've learned a ton from you guys, and I really appreciate everything you've shared with me over the past years in lab meeting and through collaborations. When you're in the PhD for 6 years, you accumulate a lot of people that you've co-authored with. So, every one on this list is kind of like an example of someone who helps bear the brunt of responding to persnickety reviewers, and helped in these pushes into the wee hours of midnight to get something out the door and get something ready for prime time. So almost everyone on this list has helped shoulder that burden in some way, and without it, I wouldn't have had enough papers to graduate, right? So huge thanks to all those co-authors for their effort and their all the things that they taught me and all the things that they helped along the way with. Likewise, I wouldn't really be able to hold down the fort at Microsoft if it wasn't for my amazing team here. These are some of the best engineers out there. I've been really blessed to be able to work with them and learn from them. Thank you for taking a gamble on me as a manager while I'm getting my PhD. And I've really been very fortunate to have such a great group at Microsoft that helps push things along, keeps Synapse ML alive and kicking, and really is pushing our work at Microsoft into new directions. So now we get to the part where we actually get to see all the fun things that we've done together over the years. So these are some of my friends at Microsoft that I've met along the way. Unfortunately, the friends at Microsoft that are here today, I don't have a photo with you guys. So today we got to get a good photo. But huge thanks to you guys for being like really my friend group and my network for the past 10 years in Boston. And it's been absolutely delightful to hang out with everyone at Microsoft. I've learned a ton from you guys. I've gotten to work with like 60+ interns over my time at Microsoft. So, and big thanks to my team for allowing me to do this crazy PhD Microsoft split and supporting me along the way. Also, I've been blessed to have a great community at MIT to share a ton of great times with at conferences, taken the boat out of Lake Como. We've gone skiing together. We've gotten to go on a dolphin research vessel for a week. We've gotten to have a ton of different fun adventures during my PhD with you all. There's also a ton of friends, my kind of like safety and social safety net that kind of keeps me afloat throughout the PhD. I've put some of the great photos from our adventures up here. You guys know who you are. We've done a ton of fun things. We went jeeping in Nantucket, mushroom hunting, skiing in the backcountry, cave diving in Mallorca, all sorts of great stuff that we've gotten to do together. And I'm so happy that I met you all. It's been delightful having you guys as a group of friends, and you really like keep me going through the PhD. I'm lucky. I feel like I met a lot of you guys like super early in the PhD, and I'm very thankful for that because I feel like I've had just a great bunch of friends to share this experience with. Kind of moving on to the family. I'm lucky that I've got like a really big, loving Italian style family that has been just there for me and supportive of me. I've got a ton of different cousins and siblings that have really been best friends and psychologists along the way too. Huge thanks to my cousins, Mike, Danielle, Nicole, Kristen, Holly, my brother and sister, Michelle and Steve, and Joe and Amy. Just huge thanks to them. I want to also give a special shout out to Aunt Lo. She passed recently this year, but she would absolutely be partying like crazy if she was here. So we love you, Aunt Lo. In my PhD, there's one person who's been like kind of there, the rock, Lily, my blueberry. Thank you for all the great adventures we've shared together. You learned how to ski for me. You went to London for me. You learned how to forage for mushrooms. We've had so many different adventures. You taught me, how to enjoy my life in a way that I couldn't have without you. You've been here for me when the reviewers are ripping me to shreds, and you've been celebrating with me when the reviewers finally let me pass the gate. So I love you, and I'm excited to spend my life with you. So thank you. Oh, it's only going to get harder from here on out. So my sister, she's been my best friend for my entire life. She's 8 years older than me, which means I'm the pain in the ass. And she's so mature that she can just like handle it, right? But because of that, she's kind of always been there, always guiding me through life. She got her PhD, which is largely why I got my PhD. So big kudos to her for really doing all the hard work first and then showing me the golden path to walk on so that I can get there with a lot less pain and suffering than she did. We've had so many fun adventures. Carrie taught me how to do PEMDAS back in middle school, and now she's co-authored like 6 papers with me during my PhD. So we've had like just a delightful, life of great collaborations, and I'm excited for more adventures to come. And she's not here today for the only reason that I'll allow her to skip my PhD, which is that she just 3 weeks ago had baby Adelaide. So congrats, Carrie. We're all so proud of you, and this baby is quite adorable. You're definitely going to spoil it. I'm going to spoil it. And so, thanks so much for being there, Carrie and Nick. I really appreciate you guys. And finally, I owe it all to my creators, mom and dad. Thanks for being there for me throughout my entire life. You guys literally were like doing my homework from day one. The original ChatGPT right there is Pops, helping me make model cars in the garage and stuff like that, building shark heads. They taught me how to ski. They taught me the meaning of hard work and what it means to push for a goal, and that I should be pushing for goals even when I'm too stupid and young to realize that. My mom also, she labeled 5,000 images for me during my PhD. She's responsible for one of my papers. It's not just a metaphor for this. It's really actually, she's pushing me through my PhD. So, thank you so much, you guys. I love you guys, and I appreciate you guys sharing this moment with me here today. So with that, thank you guys all for sitting through that gauntlet. Both a dizzyingly confusing talk and a tearful set of acknowledgments at the end. If you're interested in the math and the physics of it, you can scan that link and see a little website with all of the papers we've talked about here today. And in terms of a little bit about what happens next, this mean committee here is going to kick you out for around 30 minutes, but don't go anywhere, all right? Stay outside, make some friends. You can crack a bottle of champagne. I'm not going to judge. So you can just hang out for 30 minutes or so, and then we'll come back in here. We'll have cake, we'll have champagne, we'll celebrate, or we'll cry. Win or lose, we booze. And and then after that, after we've partied to the maximum amount for this room, we're gonna, around 6 p.m., walk over to the Watermark Kendall East for a little roof party that will go on indefinitely with food and libations. This is the address, 250 Kendall Street. The instructions will be in the party full. I'll also just walk you guys all over and bring you up there too if you stick around. It's about a 15-minute walk. There's an inside area if the weather gods don't cooperate, but so far it's been looking good. Thank you. And the party will continue until the last person leaves. And so that's the plan for today. So thank you guys all for coming so much. I really appreciate it.
Okay. That was wonderful, Mark. Both parts of it were great. So now, if you all please leave, and then we'll have our internal discussions, and then there'll be either white smoke or black smoke, and we'll let you know the outcome.